Your way to your seat, please. We're about to start the next session. So, welcome to the last session of the day. In this session, we're going to talk about the... Wait, just a second. In this session, we're going to talk about the climate DT. And what we thought we'd do for this session is, well, some of you are very familiar and even started using the climate DT. So you might not need a general introduction, but some of you might not be that familiar with the system. So I'll talk you through some of the general concept. But what we really wanted to do is talk about how the climate DT is being used already. So we'll have a series of presentations that show how they use climate DT information to derive climate impact information. So I'll kick this off with a general introduction. My name is Sebastian Malinsky. I work at ECMWF as the coordinator of the climate DT. So in this overview, I'll take you through some of the key features of the system and how we're producing climate simulations operationally. And while doing that, I'll also dive into a few specific examples to show you how the system works to already provide climate information. So what's the climate DT trying to achieve? Well, there are a few key features. So first of all, we're moving to regular production and frequent updates. So that ensures that the models are always following the state of the art and provide high-quality information. We also have a very standardized system for the simulations and the outputs, but that also allows flexibility. So since we have a well-defined system, we can also modify it based on user requirements and run special simulations or reconfigure outputs. Now, you all heard that high resolution, high spatial resolution is one of the key features of Destination Earth. And that allows two main advances here. So first of all, by having high resolution, we explicitly simulate more processes in the Earth system, so having more higher quality simulation. What it also does, it provides information on scales where impacts of climate change are felt. So what that enables is that we can directly integrate sectoral impact models in the climate DT workflow because they can straight use the information coming from the climate DT without requiring further downscaling to get to the right resolution. So with the simulations that we do with the climate DT, I want to give you one quick example on how those could be used for climate information. Take, for example, wind speed. Now, in the animation, you can see above the red line the resolutions that you get typically from global climate models, which is on the scale of around 100 kilometers. What the climate DT provides is the same information at 5-kilometer resolution. Now, the type of questions that we can answer with that is, for example, if we want to build a new wind farm, where should we build that wind farm, knowing that wind patterns change under future climate change? Now, let's have a look at the system that we set up to operationally produce climate projections and answer questions like this. So it all starts with the global climate models. We have three different models, IFS-NEMO, IFS-FESAM, and ICON, that are running on the Euro-HPC systems to produce multi-decadal climate projections. Now, these models are all producing the same standardized data stream. What that means is, independent of which model is running, you always get the same meteorological parameters on the same grid produced. These are going into a database, which is also sitting on the Euro-HPC system. Now, while the data is arriving in the database, there are a few things happening. So first of all, we have an online monitoring and evaluation framework running. And so what this does is it runs automatically a set of diagnostics that allow the model developers to monitor the status of the simulations and to see that everything is going as expected and to monitor the quality of the simulation. So that's comparing to a reanalysis, but also comparing the climate DT to current state-of-the-art CMIP models. Now, as the data stream is being produced, it's also feeding into impact sector models, or so-called applications. And I want to talk you through one example to demonstrate what this looks like in practice. So in this animation, we start with the climate DT and the wind speeds simulated by the climate DT, here shown in color shading. Now, wind speed itself is not climate information. It's just a meteorological parameter. But what we can do with an impact sector model is to translate that into wind energy. And what you can see here is the capacity factor. So in a nutshell, what this shows you is at which capacity a wind turbine is operating. So a high capacity factor means it's operating at maximum capacity. A low capacity factor meaning it's not producing as much energy as it theoretically could. So why can that be? Well, maybe we have very low wind speeds, which means a wind turbine cannot really produce a lot of energy. But also it could be due to very high wind events where a wind turbine might have to be turned off. So we can look into these types of events, for example, low wind events, but also high wind events and storms to see how that impacts the wind energy production. We can then make use of the high spatial resolution and zoom into one specific location, here location in the north of Scotland, and we can see how the wind speed evolves, but also how the wind energy produced evolves in time. And we can look how that changes from week to week, from season to season, and making use of the multi-decadal projections, also how this changes in the decades to come. Now, you're going to hear a lot more about applications in the next presentations. This is just to say that in the climate DT, we have 4 impact sector models directly embedded that run in the workflow and the EuroHPC system. And we have many more that run on the climate DT output that is provided via the data lake and platform. So at this stage in the workflow, we still have the data on the EuroHPC system, where it's not available to everyone. So an important element is that while the climate models are producing the data, it's then pushed to the data lake. And so this is happening after it passed an initial quality control to make sure that the data is complete. Once it's on the data lake, it is then made accessible via the DestinE platform, which offers many ways to interact with that data. For example, for someone who likes to code in Python, they have Insular Code to run their own Jupyter notebooks, analyzing climate DT data. There are a lot of use cases that are seen via the platform. And one service that I want to highlight here is the Polytope service developed by ECMWF, which allows to request certain subsets of the model output. So you've heard that before in the context of the Extremes DT. Same is available for the Climate DT. Allows you to directly access model output as requested. Now, what types of simulations are we producing with the Climate DT? So first of all, what is available already are our simulations that we concluded in phase 1. And so there we have 3 global models that ran these simulations. Historical simulations starting in 1990 up to present day. These are running at 10-kilometer resolution. Then we have a scenario projection that goes from present day until 2040 in the future. This is following the SSP 370 scenario, which is a rather high emission scenario. So it's assuming an increase in CO2 greenhouse gases. Then we have a control simulation. And what this is, it's a rather artificial setup where we fix everything in 1990. So greenhouse gases are not changing, aerosols are not changing. And the purpose of this is to investigate whether the models are stable or whether there's some artificial drift in the model. So this is part of the quality control, to have the control. Then there's another special set of simulations, our so-called extreme event storylines. These are run with one of the models, FS-FESOM. What we do there is we take a global coupled climate model, we run it in present day, so that's starting in 2017, but we do one modification. So we take the winds as they were in observation, so we take them from era 5, and we force the model to have the exact same circulation patterns as in the real world. So what that means is we have all of the extreme events that are circulation-driven in the model as they happened in reality. Now that on its own isn't very useful, but what we can do with this setup is we can move it to a different climate. So we can take the same setup and move it to a colder 1950 climate and ask, how would the same extreme event have unfolded in a colder climate? Would the impacts be different? Or we can ask, how would the impacts change if we would see the same extreme event in a warmer climate, a 2-degree world? Now we are in the process of phase 2, and so there are a few changes to the simulations that we are implementing. So first of all, for the multi-decadal simulations, we now run all simulations at 5-kilometer resolution and have a continuous historical to scenario simulation covering the entire period 1990 out to 2050, so it's also going a bit further into the future than phase 1. And we also have the control simulations, which are at least 10 years and also at 5-kilometer resolution. For the storylines, there's a change, which is that we regularly update the storylines to also include recent extreme events. Now I want to take you to a small example on what we can do with the storyline simulations. So what I'm picking here is the 2019 heat wave in Central Europe. And what you see in the panel in the middle is how it looked like in present day. So you can see that, especially in France and mostly in the Paris region, very high maximum temperatures were observed. So now with this setup, we can take the same extreme event, put it in 1950 and see how much colder would the maximum temperatures have been in 1950, or we can look at a warmer world, 2-degree world, and see how much warmer will the extreme temperatures be in each of the locations. What you see in the table below is just zoomed in on the Paris region, where you can see the numbers for Paris under these 3 different warming levels. You'll hear a lot more about storylines in one of the following simulations. Now finally, I want to take you through the operationalization workflow. So there are several important elements that we developed and established here. So it all starts with our so-called D suite. This is the development stage, where we put the models together, we test that everything works. And this is the stage where we can ingest state-of-the-art advances from research and feed them into the DestinE system. Now, once the development has concluded, this is handed over to our so-called E-suite, which is where the evaluation is happening. So we put all of the elements together, make sure that at the resolution that we're running in operations, everything works out, the quality is as expected. And once this is signed off in the E-suite, it's handed over to operations, where then the multi-decadal simulations that I showed on the previous slides are being produced. Now, this is an ongoing process. So once this is handed over to operations, where we have dedicated operators who are in charge of running these simulations, the model developers go back to stage 1 and say, okay, how can we now improve the models further? Like, we see the operational models, we see what advances are made in, for example, Horizon Europe projects that further advance our knowledge of the Earth system. Is there something that is at the readiness to be picked up by the DestinE system? And then that would go into D-suite, where this is being tested and evaluated, whether it's ready to be picked up, then advance to the E-suite, and once it's accepted as E-suite, it will, in a future cycle, feed into operations, further upgrading, advancing the DestinE service. Now, if you want to know more about the model simulations or see an overview of what's available so far or how to access the data, I invite you to visit the destine.ecmwf.int website. And with that, I close and hand over to Jörn.
Thanks, Sebastian. We do have time for questions. Are there questions specifically on the climate DT from what Sebastian has presented? Yeah, there is one. Can you please use the microphone?
Yeah, thanks, Sebastian, for the overview. I just wondered, when seeing the information on the aqua quality framework, what happens if the diagnostics say, like, the numbers show a degradation of the data? Is the simulation then disrupted, or is there some investigation going on? What's the problem, or does it just give the results and then it gets checked later?
So we don't just use Aqua in operations, it's already used in the earlier stages in the development, and so that's when exactly what you described is happening. If we see that something looks off in Aqua, then we either keep the simulation running a bit more to better investigate the issue, or we say, okay, let's stop, let's go back to the drawing board and see what caused this. In operations, we have Aqua running, but ideally there should be nothing surprising happening because we properly investigate the models beforehand in development and in the eSuite where we do run simulations to make sure that this is working as expected. So in operations, Aqua is really mostly there to give an overview of what the quality is of the ClimateDT models. We are in the process of deploying this as a dashboard on the DESP, so that the Aqua diagnostics can be checked by any user. Ideally, before you would start deploying a new application, what you might want to know is what's the quality of the models for a specific parameter. How good is it at representing temperatures or precipitation? So that's what Aqua is doing. So it's showing you maps or time series of how well the model does. But it's also informing further model development. So while a small error might not be a reason to stop a simulation, it might be a reason to further investigate whether we can do something to the model to improve this in a future cycle.
Okay, thank you.
Other questions? Yes, there is one.
Thank you. Yeah, thanks. This was a really helpful overview of the ClimateDT. I just wanted to comment, this overview is kind of lacking from the websites, because I've been looking for some of this information of the different scenarios and their meanings, and I think there's definitely some room for improvement, so we can find this offline as well. But this, I'm so happy you gave this presentation. Thank you.
Thanks for the feedback. I like to point to this website because we're constantly updating this, and we're trying to have the current status represented there, including a description of the scenarios. But yes, this can be further improved, and we're working on that.
Thank you. I see no further questions, so then we'll thank Sebastian and move on to the next presentation. This one is by Sushavan Gost from the BSc, and he'll be talking about the energy indicator application developed within the ClimateDT, and tell us a bit about the user engagement and the experience.
Hello, I'm Sushavan. I'll be talking about energy indicator application and its user engagement and interaction on behalf of energy indicator application team at BSc. So just start with, we see that the global wind capacity and generation is rapidly growing and almost growing at an exponential stage. But at the same time, wind energy is vulnerable to climate change. And here comes that Climate Adaptation Digital Twin initiative, which gives us the impact of climate change and different adaptation strategies at an unprecedented resolutions globally. And this has been done with the use cases, which actually translate this climate data into tailored insight. So we know that the climate information is being transferred into tailored insight using different applications. But to better understand the tailored insight, we also have to have a look on what climate information is being fed into these applications. And thanks to these high-performance computing facilities and the Earth system model, and already Sebastian already talked about these are the different coupled simulations is currently being run and is being fed into the energy applications. And when we talk about the energy applications, we are currently have certain indicators like wind speed at half height, capacity factors for the different turbine types. So these are the production side. And also we are looking into certain extremes like high wind events, low wind events. And we are also developing some of the demand statistics like heating degree days and the cooling degree days. And all these indicator applications output is user-oriented. That could be the data files, that could be the graphic visualizations, And we are doing an extensive amount of key user engagement and interaction to improve the different indicators and as well as their experience. And we do this by providing local to regionally tailored insights globally. So starting from the bottom, starting from the top left, we are providing the wind speed at 100 meters. We also providing the capacity factors. We are also doing the percentage occurrence of the low wind events and the high wind events. And not only that, we are also focusing on some of the potential wind energy regions like North Sea. And we have users, they are much more interested on some of the specific location, let's say Moray East, what is the wind speed distribution for a week, or what is the capacity factors of their already operational turbine specific. So those information we are also doing. And how we are engaging with the other key users. From the phase 1 to phase 2, we are attending many conferences, many workshops and meetings, and we are presenting posters and talk. And some of the experience, let's say from the Climate to Europe web festival, we do an online interaction with the users. So we asked about their background, and we see they come from the climate scientists to researcher, NGO to government organizations and the policy. So we get a good amount of background of our users, and also their scientific domain or the sector or the area of expertise. And also we asked certain specific questions that how they used to work with the climate DT data. And there is a good amount of response from the energy to other use cases also. And based on like what Sebastian was also mentioning, we asked some topical questions like what is the need for the future installation? Do they think that the climate change things is important for the future installation of wind farm? And we get a clear consensus of their agreement. And also, we also have some more response from the user that they want to use the output of the climate data. At the same time, they are much more interested to use the use cases in general. So now coming to our key user specific engagement, we have one key user. That is the Ocean Wind. They have an operational wind farm, offshore wind farm at the Moray East regions. And for them, we are doing a user story, and we ask many questions. Some of the key questions we asked that what are they doing with the climate DT? And they are saying that they are planning to use this kilometer scale simulation for operational of wind farm at their regions, and they are much more interested on the capacity factor histogram to extreme events and all these things. And also we ask some other questions like how this climate DT is adapted to their company's needs. So there is a clear response from that they never used this type of data. They usually use the historical data sets, but they want to use this high resolution data set for their operational framework, and also they want to incorporate these things to the financial model. So not only the private sectors, we are also engaged with the research organization and the academics. And there is like JRC, they are interested to use this data set for the energy grid sorts of simulations. And we also have some sorts of preliminary engagement with other organizations as well. So now coming to our future developments, we are not only interacting with the users, but we also take the user suggestion, like Ocean Wind suggests us to develop some of the other indicators also. So we are doing those indicators like percentile-based indicators or the Windows sorts of indicators. And in future, we are going to use some of the solar indicators as well in the energy applications. So as there are many questions regarding its scientific assessment or trustworthiness, to increase the trustworthiness of our applications output also, we are doing a rigorous scientific assessment side with the Aqua, and these are the future development we can expect in the next cycle. So I will have a poster that is in the back side of the room, And if you want to be the key user, next key user, you can connect with us. So thank you.
Thank you very much, Sushavan. Maybe stay. So it's time for some questions. If there's any quick question from the audience or online, I'm happy to take that now. No? Okay, we'll also have a session or a short time period in the end of the session where we can take questions about all of the presentations. So we'll come back to a more general discussion in the end. So thank you. And we'll move to our next presentation given by Aparna from the Helmholtz Center for Environmental Research. And she'll be talking about adapting to future droughts and floods.
Yeah, thank you, Sebastian. So today I will be talking to you about the HydroLAN application that aims to provide information on climate change and adaptation to terrestrial hydrology, that's floods and droughts. So I would like to start with an old story. Climate change increases both the intensity as well as frequency of both floods and droughts. And for example, current climate information systems or current climate models predict, for example, an increase in high flows or floods in the western and northern parts of Europe and reduction, for example, in more droughts, for example, in the Mediterranean region. However, it's also important to note that a lot of these impacts of floods and droughts usually happen on the local scale. And furthermore, in the future, not just increases in the intensity as well as frequency of these events, other factors like increase in population or land use changes could also increase the severity of these events. For example, you can see over here that population is also predicted to increase in many regions. And if these are in the regions which are more exposed to floods and droughts, this could actually increase the impact of these events. Current climate information systems have several gaps, as you also may have heard in the previous presentations. And within the HydroLAN, we want to address these gaps, 3 important gaps. So first is we want to provide more high-resolution information. Currently, for example, models like CMIP, they provide close to 100 kilometers spatial resolution, which may not capture floods, which usually happen locally. So the HydroLAN application uses the hydrological model, which is developed within the UFZ. And the information, so it's able to directly stream the climate model data into the application and works at the same spatial as well as temporal resolution as the climate models, which is like 5 kilometers spatially and hourly temporal resolution. Currently, within this field, we don't have an active involvement of users, and usually the users are involved towards the end of the chain, whereas we are co-designing the application with water suppliers, and any indicators or information that's provided can directly be used within their decision-making process. Currently, we also don't have so much interactivity with the system wherein these so-called what-if scenarios can be built. And within our hydrological model, we actually have the capability to provide what-if scenarios. For example, a user can see how they can build a reservoir or build dams or change, understand the impact of changing the reservoir height, for example, and see the impact on river discharge ultimately, and really plan their policy decisions based on that. So just in summary, the HydroLAN application directly streams information from the climate models, and it can provide key hydrological variables like river discharge, runoff, soil moisture. And this is co-designed along with users, and we are able to provide indicators. Furthermore, we also can include what-if scenarios within the hydrological model to understand the impact of policies on these variables. Now I would like to talk more on the results as to how we actually were able to use some of the results from the current climate models and how this can be actually used by users. So for example, one of the climate model types, like how Sebastian was talking right now, is on these storyline simulations to really see how an extreme event would play out in a warmer world. So for example, if we think of the Valencia floods last year in 2024, we can actually see, for example, precipitation, which was one of the main drivers of the event, see how this would look in a warmer world. And we see that there is actually also a shift. First of all, you see much more granularity, much more local impacts of the precipitation, and you see that there is a reduction in precipitation in some areas, whereas it increases in other areas. And this could also be important for adaptation planning. While this is in the climate model side, we also see on the impact side, there are changes in runoff and soil moisture, which could impact different sectors, from flood planning to urban flooding, as well as to agriculture. For example, when you see changes in soil water in different layers, this could be impacting, for example, agriculture in the top layer. This could really be important information to understand how this event plays out. Along with that, we can also build indicators based on long-term data. For example, using long-term stream flow data, we can understand the high flows. And we can, for example, define floods as when the high flow value is increased. When a historical high flow value is increased, we can define this event as a flood, and then understand how the frequency, intensity, as well as duration of these events change with climate change. So for example, we can use a historical data to calculate these indicators and see how this changes in due to climate change. For example, we see in Germany, there is some kind of dynamics. In the eastern part of Germany, there are increases in high flow, whereas in, for example, Spain, the high flow decreases. And this can then be used to understand the impact on different sectors. For example, on trade, like for example, these could also be important for like shipping and all of these industries. This information could then be used directly within their decision-making process. I would like to just talk a little bit about the what-if scenario. So an example of a use case on a what-if scenario use case that we are building with one of our users. So an example could look like we could provide a separate catchment setup or a what-if scenario setup in a specific catchment. For our user, they requested one for in the Black Forest Mountain region and actually see how changes in forest cover would impact runoff. This could then be used by them to understand the changes in water quality. So within our model, we can actually change the forest cover to reflect the current forest cover, which let's say is, for example, 60%, and change it to reflect a worst case scenario, which is much lesser forest cover, or a best case scenario that we really recover all the forests. And then based on the delta within the current forest cover to the best and worst case scenario, we can actually understand the impact of these policy scenarios on the indicators or variables that is of interest to them. So I would just like to conclude by giving you a small summary of what I said. So we are able to provide high resolution data in 5 kilometers spatial as well as hourly temporal resolution. And we can really provide sort of this bespoke information, not just on variables and climate indicators, but also provide separate what-if scenario setups for the users. So if you have any questions, I'm open to answering it, and please contact me in case you want to be a user or you have further clarifications on this. Thank you.
Thank you very much. The floor is open for questions from the audience. I think the point that you made about the what-if capability in the impact sector model, that's quite interesting, to show that we have different stages in the modeling chain where we can play what-if scenarios. And I think the one example that you showed already is quite promising. Do you have any other examples that you think could come next where you could use that what-if capability on the hydrology model side?
I mean, I think one which we're really interested about is really with respect to the reservoir planning. We're not sure. It's also, I think, to do a lot with our model development. I think we do have a branch of our model which can include reservoirs, but we're not sure how it would play out in an operational system. So I think this would be another interesting use case, especially for water suppliers, to include this within within their what-if scenarios. So I think this is one more thing that we would like to include. But I think land use change is something that's really requested by a lot of users. So one is forest cover, but it could also just be increases in urban areas or more agricultural, more land use more for agriculture. I think one of the what-if scenarios that could be a bit more detailed is to really include different kinds of crops. And I think this would also be interesting for some of them. But I'm not sure technically how far we can go down, and this is something to be discussed, but yeah.
Thank you. Any questions from the audience before we move on? No. Okay, and thank you again. And our next speaker is Dick from Vito, who will talk about urban heat management. Oh, sorry?
Have you not uploaded your presentation?
No, it was there in the morning.
It was there, eh? I think so.
Okay.
Right, let's rearrange and ask Kat up here next, where we try to sort out the reason why this is not there. So sorry for that change in schedule. So then we'll have Kat from the Barcelona Supercomputing Center talking about the storyline simulations.
Okay, great. Hi, everyone. I was going to say thank you for staying to the last presentation, but I'm actually not the last presentation now. But thank you anyway for staying. My name's Kat, and I'm going to be talking to you about the storyline simulations and how we can use them to understand the impacts of warming on extreme events. And I know we've heard quite a lot about the storyline simulations already today. They've come up in quite a few presentations. But I'm just going to go into a bit more detail about what the storyline simulations actually are, how we run them, and what we can gain and what we can learn from analyzing the results. So for those of you who are familiar with normal Earth system models, global climate models, the way they're normally run is you set up a spin-up, the model kind of finds its own equilibrium, and then it runs. In projections, you let it run for decades. In that way, you can gain insights into how the climate is changing over long periods of time. But we can't tell you what the weather is going to be like on a particular day in 20 years' time. Now, the storylines are a bit different because that's kind of what we do. Rather than letting the model run and find its own equilibrium and create its own weather, we force the model to recreate the observed weather that we had in the last few years. So in this case, we've run the simulations from 2018 through to 2024. And what we do is we fit the upper atmosphere to match exactly the data we have from Error 5 reanalysis. So that's kind of observational reanalysis data product. And we can say, okay, we want the upper atmosphere to recreate the wind patterns that we saw over this time period. And that way we can see exactly the weather that we had. And as Sebastian was saying, that in itself isn't actually interesting. But what's really novel about these simulations is we put them into different background climates. So we run the same weather in A, the present day climate, B, in a cooler climate around 1950s, and also in a future climate where we're expecting about 2 degrees of warming in a global average. And that allows us to understand the impacts of anthropogenic warming on a lived extreme event that we were all present for. So one of the main questions when you run these types of simulations, or any simulation, is do they work? I mean, in short, I'm going to say yes. I think they're actually very good, the simulations that we've got. This is looking at a global scale, some validation that we've done comparing against Error 5. I know we are nudging with Error 5s. We do expect them to compare well with Error 5. But I should add that these variables that we're considering here are not nudged variables. We nudge the winds in the upper atmosphere. We don't nudge temperature, sea surface temperature, precipitation, and geopotential, which is what we're showing here. And overall, we get very good mean bias, usually around 0. We can see in some cases we're getting larger biases. For example, the sea surface temperature, we've got larger biases in the Southern Ocean or in the equatorial Pacific, which is to be expected because these are regions where you've got strong ocean currents and very complex ocean dynamics. And the ocean models that we have actually are able to produce their own ocean eddies. So we do see stronger biases in these regions. Also, for the precipitation, you can see around the equator, we do get larger biases. And this is also due to more convectively driven precipitation in these regions. Because what we're nudging are the winds and more dynamically driven systems, whereas in regions where convective systems dominate, we are going to see larger biases in these regions. But at a global level, the validation looks pretty good. And then we can start looking at actual local events. So that's the point of these simulations, right? To understand what was the impact of warming on an event. So this is taking an example from Hurricane Helene. This was an extreme storm that occurred over the Caribbean, east coast of the US in September last year. And again, this is still looking at validation. And I should add, the validation that we're looking at here is for the actual scenario. We're not validating well, we do, but here we're showing the validation for the actual scenario, not the historical or the future scenario. And what you can see on the left, we've got Error 5 data. And then in the middle, we also have a high-resolution observational product called MS-Web, which has high-resolution data available for precipitation. And then on the right, we have the IFS-VSIM storyline simulations. And what we can see is a very good agreement, both spatially and quantitatively, with the amount of precipitation that fell during this event. And now I'm actually going to move to a little video. I'm going to stop talking for a couple of minutes, which is just a nice visual representation of what we can learn when we start comparing the different scenarios in the storylines. So this was a video from Jan at AUI. And there should be sound.
Using novel storyline approaches, the Destination Earth initiative helps explore how recent extreme events would play out under different climate conditions, past, present, and future, providing actionable insights to support adaptation to climate change. Let's look at Hurricane Helene, USA, 2024. In September 24, Hurricane Helene caused widespread devastation, primarily in the southeastern US. The storm resulted in over 230 deaths and up to $200 billion in damage. In this simulation, we will take a closer look at the Asheville area. The high-resolution climate model simulates the extreme weather event and its impact on precipitation accumulation. Next, the model simulates the same weather event under past 1950 and future plus 2 degrees Celsius conditions. How has climate change from 1950 to present influenced this extreme event? In the selected area of Asheville, accumulated rainfall has increased by 20.2 litres per square metre compared to 1950 climate conditions. This represents a rise of 8%. Now, how would accumulated precipitation change for this event from the present to an even warmer future? For the selected area, an additional 5.8 litres of accumulated rainfall per square metre are projected due to climate change. This corresponds to a further rise of 2.1%. Learn more about the initiative and its storyline simulations of recent extreme events. Visit destination-earth.eu and destinee.ecmwf.int.
Okay. So yeah, that was a really nice visualization where we can understand what we can learn when we start to compare the different scenarios. And we've done this for multiple different extreme events. This was a quick analysis that we did for the Valencia floods. They also came up in Aparna's presentation. I'm actually going to skip through this in the interest of time and move on to another extreme event that we looked at, which was Storm Gloria. This was another extreme storm event over the east coast of Spain that actually occurred in 2020. Similar dynamics to what happened last year with the storm events around Valencia, although this one was over about a 5-6 day period, and it had a slightly different spatial location. But we conducted a similar analysis where we looked at the amount of precipitation that occurred in the 3 different scenarios. So in the counterfactual or the historical, the cooler simulation, which is on the left, the actual simulation, which is in the middle, and the future simulation. And we conducted a similar analysis. So here we said, what was the increase that we saw in extreme precipitation, so accumulated precipitation over 150 millimeters, when we look between the 3 simulations. And in this case, covering the area that we can see here, we have around 4.5% increase from the counterfactual to the actual, and then an even greater 33% increase when we look into the future. And I think what's really important here is there is uncertainty in these simulations, and I think it's important not to focus too much on exactly the changes in spatial location. But what's really powerful about these simulations, it's a very tangible way that we can understand how climate change is impacting these extreme events. While we can argue over percentage details, I think as we start to build up a catalogue of analysing different extreme events globally, we can see very similar patterns beginning to emerge. We can see the same patterns in intensity of droughts and intensity of storm events. And we can use that as a way to connect with lived experience on lived experience of extreme events and explain to stakeholders, to people who work in insurance or different policymakers, how there are non-linear relationships between 1 degree of warming globally and the intensity that it causes in an extreme event. We did a little bit further digging onto this event, and again, this is going onto from global information to local scale. I'll go back. We analyzed the intensity of precipitation in these 4 regions over Girona, Valencia, Alicante, and Ibiza. And again, this shows that while we're seeing more homogeneous changes in the top line of atmospheric moisture, kind of around 6% in all of the regions, we see quite non-linear changes in the precipitation. And in some cases, we saw precipitation increase by up to 45%. So again, this goes back to this non-linear relationship between how 1 degree or 2 degrees of warming can then much more severely impact the intensity of an extreme event. I won't go through the details of this slide, but I just wanted to add, this is connecting to the talk Aparna just gave. As with all of the data that's being produced in the climate DT, the storylines are no exception. We can then run all of these extreme events through the different use cases. Here we run them through the hydrological model that Aparna presented. We've also got the wildfires use case, the energy use case, and other hydrological models that we can look at. So again, we can use these use cases to understand more the downstream impacts, not just looking at meteorological variables, but if we extrapolate further downstream, what can be the impacts of these extreme events. And I'll leave it there, but thank you for listening, and let me know if you've got any questions.
Thank you very much, and I open the floor for questions. Yes, please.
Good afternoon. I do have a question regarding the issue of does it work? I understand that for validating that issue of does it work, you would search 2 different atmospheric setups that are at different points in time that are fairly identical or very similar, and then run one of them on the conditions of the other one, like changing the temperature. Have you done that?
So I'm not sure if I fully understand the question. The way we do it is we keep the same atmospheric dynamics for all three scenarios. So we have exactly the same atmospheric dynamics, and then we change the background climate by changing the forcing, so the background levels of greenhouse gases, which will change the temperature.
No,
that's not what you're asking.
No,
okay,
that's not what I'm asking.
Okay.
I'm asking about the validation of the approach. So in order to validate this approach, I understand that you would take a scenario that has repeated from the past, and then you run both scenarios, changing in one case the background temperature and reproducing the same results that you had in the past for another scenario that was fairly identical. So you need to find those two scenarios in the present and in the past that have had very similar features. Have you found that and done that?
I'm not entirely
Maybe I
sure.
can try to help here.
Yeah.
So I think when you say scenario, what you mean is an extreme event, like a blocking event or a storm, right?
It can be an extreme event, or it can be a global setup of the circulation, atmospheric circulation, which I don't think it will happen ever.
Well, so it's kind of by construction, we ensure that it's the case in the model. It's not that we have to look for something similar, because with the storyline approach and the nudging, we force the model to be similar.
Exactly. But then we cannot talk about validation. That's just an execution, not a validation per se, because when validating, we are comparing with some actual result.
But for the validation, what we're doing here is we're nudging the upper level winds in the atmosphere. And then we want to see how well other meteorological variables fit the observations. So what we were showing there was the mean bias between the model for four different variables and the observational data or reanalysis data for error 5.
Okay. Thanks.
Niels.
If I understand right, I think he is asking whether we have verified it within the already known envelope of warming, whether we can nudge and then look in the, say, warmer part of the recent climate, whether we have been able to identify the increase, say, of 5 liters per square meter already within, say, a known scenario.
Okay. I think I understand better now what you're saying. I think this work is ongoing. We have started to look at how we can identify the changes between the present and the future climate and actually validate them with events that we've seen. And there are more details if you look at the reference here, they do this type of validation, but I'm probably not the best person to answer that question.
I think we can also continue that discussion either offline in the coffee break, but we're also generally happy for any type of feedback. So if there is some feedback like this that you have for the system, you're welcome to submit that, and we'll get the experts on it to answer it. Do we have any other questions on the storylines? If not, then let's thank Kat again, and I invite Dirk back up.
So there goes my professional image. Good afternoon, everyone. I'm Dirk Lauwaard, a researcher from VITO, a Belgian research institute. And in my presentation, I would like to talk about the stakeholder engagement activities in 2 Destination Earth projects to which we have contributed over the past year, focusing on urban heat management. Tecnalia, a research institute from Spain, has led one of these projects, and they have also contributed to this presentation. The first project we did delivered 100-meter resolution urban heat stress indicator maps for the demonstration cities of Prague and Lisbon. And we also looked at the impact of a range of adaptation, heat stress adaptation measures using climate information from the climate digital twin. The second project, which was led by Tecnalia, delivered a more generic adaptation modeling framework, again focusing on heat stress. And this project focused on the Basque Country in Spain. And now, recently, we have started a new Destination Earth project where the idea is, together with Technalia, to come to a real urban heat stress service on the service platform, providing high-resolution heat stress maps and also actionable insights to inform stakeholders on urban heat stress adaptation strategies. The motivation for our work is to support the European Union adaptation policy to increase local resilience to heat stress, and also support local administrations to take the most efficient heat stress measures specifically focusing on the most vulnerable people and locations in their cities. And at the same time, we want to demonstrate the added value of Destination Earth to tackle urban heat stress, which consists of course, these very high-resolution climate information, but also the flexible scenario options, and being a full integrated service that is useful for this type of work. On the right-hand side of the slide, you can see in the meantime some example of our modeling output. This is for the city of Prague, showing the hourly urban heat island intensity during a heat wave period, and you see that the urban heat island intensity can reach up to 8 degrees Celsius during the night, which has strong implications, of course, for the health of the people living in the city. But in this presentation, I wanted to focus on the stakeholder engagement in our projects. And in the first project, besides the demonstration cities of Prague and Lisbon, also DJ Regio was involved as one of the main users. And we were able to gather a broad stakeholder community for this project, including European Directorate Generals, European institutes, the World Bank, 4 city networks, some city supporting consultancies, and also some Belgian and Flemish stakeholders. And we interacted with our users through a series of meetings and telcos, and we organized 2 workshops with them, first in the beginning of the project to scope the project and to co-create the service, and then at the end of the project to get their feedback and suggestions for improvement in the future. Through these interactions, we collected a lot of useful information, assessing, for instance, the user needs, also looking at which climate data they are currently using, which tools they are using to handle this data. We performed a data gap analysis. We informed the users about Destination Earth, and we compiled a detailed list of user requirements for our modeling work, including spatial extent and resolution needed, time horizons, etc. And like I said, at the end of the project, we collected feedback on the results and functionalities they would like to see added in the future to our service. And a lot of this interaction was also done through online Miro boards, which worked quite well for this purpose. The lessons we learned from the stakeholder engagement in this project was that there is certainly a strong need for an operational heat stress service, as more and more European cities face challenges due to heat stress risks. And the stakeholders really liked our detailed maps that we could provide with the service. And in the bottom half of the slide, you see an example of this, showing the average number of tropical nights for the city of Lisbon, with on the right-hand side, the reference situation, where you clearly see that the urban heat island of Lisbon contributes to much more tropical nights in the urbanized areas compared to the rural areas. In the middle panel, you see the impact of a quite ambitious heat stress adaptation scenario, which is able to reduce the number of tropical nights for the urban regions to, let's say, the rural values, more or less. And this is certainly needed, because if you look at the projections from the climate digital twin, you see that even in 10 to 20 years, a huge increase in the number of tropical nights can be expected in Lisbon. So it's certainly something to take into account for the city. But our stakeholders also highlighted some areas for further improvement, such as extending the geographical coverage of the service to ideally all European cities. Also, even refining the spatial resolution. This is at 100 meters, but they would like to see street-level details in the heat stress maps, because that's where the local stakeholders operate. They would like to see the time horizon also increase beyond 2040. And they also noticed that, okay, it's nice to have a heat stress service, and there is an air quality service and other service, but they would like to see more integration. Also, that they have a one-stop shop for all their needs in urban planning. So that's also something they highlighted. Let's go quickly to the second project I want to talk about. It's the General Adaptation Modeling Framework, which was a bigger exercise led by Deltares, who focused on flooding in their Lot 1 project. And we were able to gather an impressive amount of Tier 1 and Tier 2 stakeholders for this exercise, including governmental organizations, research institutes, private organizations, with which we interacted again through meetings, webinars, questionnaires, to gather a lot of useful information. Specifically for the heat stress project, which focused on the Basque Country, a lot of local and Spanish institutes were involved, including the Basque Meteorological Agency, who performed a model validation exercise for us in the project. And it was really helpful to have these local health experts on board to come to a useful service in the end. Similarly, as in our first project, we again collected all this information from the users. We informed them about Destination Earth, and we really co-designed the service with the health experts, looking at which heat health indicators they want to see included, which threshold values we needed to use, which climate adaptation measures we had to include in the service that made sense to them and which was something that they could work with. And then Technalia, they made the effort to combine everything into an interactive online web tool, of which you see a screenshot over there, where users can really play around with the adaptation measures, with the climate scenarios to see how it will evolve for their region and what can be done about these heat health indicators. The lessons we learned from the stakeholders in this project was that, if you're working on a heat health ecosystem, you really need this in-depth local knowledge. Otherwise, this will not be picked up by the local people. So the co-creation process is really essential if you want to make the service again for another region or you want to go to other topics. You really need to go through the co-creation process again. Again, they expressed the need for an operational system, but they also insisted that it should not only include quantitative climate information, but also socio-economic data and also data on other health determinants like air quality, mobility, behavioral aspect, etc. Again, they said that, okay, these high-resolution heat stress maps are really key to start working on heat stress adaptation, and they encouraged us to go to other areas in Europe to reproduce what we have done. And this is what we aim to do in our new project. So we want to build upon the lessons learned from the previous ones and come to an integrated service on the service platform, also linking to the data lake. And we also want to increase the spatial resolution of our modeling work and really go to street-level detail, as you see an example there for the city center of Brussels. So if you want to know more about our work, please come and visit our poster in the back, I would say. And thank you for your attention.
Thank you very much for a very interesting presentation. I have two questions. You said Tier 1 and Tier 2. Do you have a more specific definition of this type of stakeholders? That's question number one. And question number two is, have you made some sort of estimate of how much resources in terms of time and work power that goes into the co-design interaction with the stakeholders?
Let me start with the second one. This co-design process takes time indeed, and it really depends a bit on the local stakeholders and how much time. But it's months of time to talk to them, to get to know what they need, and have a few meetings. One meeting is not enough. You need several meetings, and you have to count on months of work. That's for sure. But if you want to have something that is really picked up locally, you need to go through that process, in my opinion. And then for the second point on the Tier 1 and Tier 2, I was not too involved in this, but I think the Tier 1 stakeholders were the ones that were really attending the meetings, really co-designed everything, and then the Tier 2 stakeholders were the ones attending the webinars and things like that. I see Nieves nodding, so I think I'm correct. Yes.
Any other question to Dirk specifically? Okay, then you apologize. You can stay up here, and I'd like to invite all the other speakers back up on here so we can put them on the panel. And now we have another about 20-25 minutes to have a discussion, more generally on understanding the climate risk using the climate DT. So can you please come back up here? Where are you? Can't see, yes. Whoa. Good.
I made it. You didn't warn us about this part.
Yes, and also the online audience is invited, or I guess you in the room can also use the Slido. So we'll take the Slido questions also as they come. But I think to get us started, we've thought about a few questions to get this kicked off. Sebastian.
Yeah, I have 2 questions, and you can pick, each of you, which one you want to answer. So based on your experience, is there something that you would highlight that worked really well in your experience, or is there something that's missing? I know you all talked about the feedback that you got from your stakeholders, but is there something that you want to highlight as the one thing that worked or that didn't work and should be improved? You can also answer both if you have an answer to both.
You want to start?
Maybe, yeah. Okay, yeah. Maybe I can try. So I think for us, especially recently with one of our meetings with our stakeholders, I think they were really interested in these what-if scenarios. And I think that this is something that really works, especially the fact that these are really high-resolution information, so we can really make these local setups and try out these different scenarios. So I think these what-if scenarios, as well as the storylines, were really interesting to them. So I think that this new kind of working with climate data is, I think, pretty nice. Yeah, maybe this is a good experience. I'm not sure about the other one.
Yeah. For us, is like that. That like energy system is a very complex thing. There are many people are working on. Somebody is interested on grid modeling. Somebody is interested on predictions, and we are. In the climate DT, we are working for the future climate security projections, productions, and all these things. So one aspect is that we are producing very high resolution data, but one challenge is that someone is interested to incorporate this to grid modeling. So that is a challenge, and we are actually interested how we can put this high-resolution data to the grid modeling, or somebody is interested on some regional work on that demand or something that we are interested. But this is quite challenging how we can incorporate these things in that sense. And the blessings part of that climate DT is that we are having the high-resolution data, but sometimes we faced some questions of do we need very high resolution data for the projections and all these things. So as we get the chance to work with the high resolutions and the coarser resolution state-of-the-art like CMIP and Cordex, so we had a chance to compare these things and put the context that we really need high resolution data and the scenarios to come to better implement these high resolutions data set.
Kat, do you want to comment?
Yeah, I will just elaborate on what was said before. Also in terms of the energy use case that we're doing at BSC, I think what's been a challenge for us is really understanding, as Shushvan was saying, what really are the needs of the users and how the different ways this type of data is currently being used. Is it being used? And how can we really make sure that we're adding value to the community? So I think in that sense, having these types of events and being able to connect with users, and we've had some really interesting discussions already today, that's really useful because it also allows us to make sure that we're following that co-design approach and really trying to tailor the output of the use case to what users need, which can be quite challenging.
Yeah.
And for my part, I can say that what was seen as an improvement by the users, but especially for the city of Lisbon, was really they have very complex terrain, and the climate digital twin is really much more capable than other GCMs to solve this and take this into account. So you really get better estimates, I think, for the future. But on the other hand, we had a lot of scientific people also in the stakeholder committee, and they also want to see this ensemble approach. They want to see comparison to CMIP6, and just one scenario for them, that was not enough. Yeah.
I think that's a recurrent theme that we've been hearing a lot. Looking around the room, if there's someone who wants to break the ice, or if we should let Sebastian ask his other question. It's getting late. Yes, Sebastian.
Right. So the other point would be, what's the next step for each of you? Either is there a concrete next step that you're already starting, or is there something that in an ideal world, this is what you really want to do next? And there's maybe also a chance to invite others to comment. And what is the next thing that you would like to see based on what we've had in the presentations? But maybe you can also reiterate the one highlight that you want to give as a next upcoming step.
So Neves wants to take a first stab at that. So I suggest we take her point, and then you can think about your answers a little longer.
Yes, I wanted to ask you about because at the end we are here really to provide option for adapt. So we are here to look for strategies, measure so that regions and cities can better adapt and minimize the different risks that you are pointing. I have seen in your presentations really nice picture of what is going to happen if we do nothing. And I wanted to ask you maybe what is the limits of adaptations and the real practical and real potential for adaptation in cities. For example, in your first presentation, you were putting very nice picture on different possibilities of adaptation, but which are the realistic options for cities, and what happens if that is not enough? What else we can propose to them?
Dirk, do you want to start on that?
Yeah, a good question here, because I think that's what climate digital twin is made for, I guess, for this type of question. So that's also what I would suggest as a next step, is to really look into what is the maximum we can do, and then what can be done, and how far do we get with that, and what can we not do with that, and that we can inform the users about that. Yeah.
Anyone else wants to try to complement? Kat?
Yeah, I'll give it a go. I think from my side, what's really important at this stage is we get the community to start working with the data and really understand, what is the added value, and also where are the limitations, how can we develop better the uncertainties that we have in the models, start doing these comparisons, and then we can start looking at, if we start implementing certain adaptation scenarios, how is that going to look and what can we minimize? But I think at this stage, doing more work to understand the data and getting users to work and see how it fits with their models, that's when we're going to be able to answer those questions.
I think you, Kat, also mentioned that the link to understanding the user needs was one of the main challenges in response to Sebastian's question. So what, maybe to turn that around a little, what would be the thing that would most help you make that connection more easily? You wouldn't necessarily need to implement yourself, but that's something that would need to happen in order to facilitate that.
It's a really good question. I think obviously the easy answer is these kind of events, because it's nice to meet people in person and understand what they're doing and how they can use the data. And then I think it's figuring out which type of communities we're also trying to engage with, because there's very different types of users in the consortium that we've seen today. There's an academic branch, there's more political branch, policy branch. So it's also just about making people aware that this type of data is out there, getting them to use it and slowly beginning to gain wider visibility and having more interactions, really. But I think these types of events and going to conferences, speaking with people is really a good way to start these conversations.
Okay. Bente wants to come for seconds.
Yes. So you have shown applications to the climate digital twins here from various perspectives. Do you see any, cross-learning from across your different work? And is there a possibility to gather some best practices based on your different perspectives?
Yeah. Let me put you one context. What Kat is also doing storyline simulation, but she is also interested on the small island studies, which is currently quite impossible to do with the state-of-the-art simulations like CMIP or Cortex. So we are in a process which Sebastian was also asking, that what is the future things we are looking into. We are also taking the advantage of this high-resolution kilometer-scale simulation to study some of the energy future potential for some of the small island areas, which is important in terms of research, scientific sorts of thing. At the same time, in terms of policies, often these islands are getting isolated from the original mainland countries. So they have separate grids and all these things. So this type of studies, like small island study for the energy use case, can give us climate resilient grid operation and climate sensitive renewable energy source of production and projection to that island. So that is one cross learning you can right now I can thought of. Yeah, thank you.
Okay, maybe there are user or other stakeholder institutions in the room or online that also want to comment on how they would feel they could best be supported in making that bridge to exploiting, communicating their needs better, or exploiting what has been presented in terms of what's available. So if you have comments there, please bring them up. In the meantime, we do have one first Slido questions. When talking about community involvement, who do you mean? Local governments, and who can people that are most at risk of hazards be? How can they be included in the co-creation process? Sebastian, do you want to comment on that?
Or I'm not sure if it's me or
panel,
rather...
you should be on the panel too, it just only has 4 chairs, so...
No, I think I would hand that actually over to the experts on the interactions with stakeholders.
Yeah, I think from our point of view, community involvement, it depends on your specific interest. Speaking from the energy point of view, it's maybe private companies who are working in the energy sector, or the JRC, for example, who are doing research into energy security. So it depends. I think the community is very broad. There are lots of different interests. And I think it kind of goes back to a question that was raised earlier in the session, when someone from Hector Renew asked kind of, is there a framework that people who are working with the data can follow to make sure that we're following the same standards and the same type of analysis? And I think that's really important, just in general, to be transparent about how the data is being used, how it's being processed. And when users go on and try to access the data, be able to see the tool chains that other use cases and other analyses have used to get to the end results. So I think it's also something on the consortium to facilitate that kind of ease of uptake from the different users, because there are varied needs, but I think some of the processes of analyzing data can be quite similar.
Maybe at a slightly higher level, I can also comment on that question, that of course the community does involve users at all levels, not just local governments, but also EU level, national governments, could be international institutions or conventions that could play in this, and there are interests, and bringing them, engaging them in the table in these discussions is part of the objectives. It's actually a little easier at the higher levels because there are fewer cases. When you go to the communal level, then it becomes very difficult to scale into the breadth. But this is what we mean. In the meantime, there is another question: how the connection between the extremes and the climate DT works. That I think, Sebastian, you may be able to comment on.
Yeah, I think that's a very good question. And really what we have for the first time here is the opportunity to look at weather to climate timescales in a seamless system, where if you think you have a wind farm running somewhere, you can use the extremes DT to see how an oncoming storm would affect your energy production in the next few days. But then maybe motivated by that, you might ask, okay, how much worse can storms get in the future climate? And then you would switch over to the climate DT, use your same model for the wind farm, plug that into the climate DT, and see how future storms might affect that installation. So I think the strength here is really that we have a seamless system that allows you to transition between both. Maybe someone else wants to comment on their specific use case and whether there's any connection there.
Maybe just a short comment. Yeah, a short comment from my side. So I think even for, I think somewhere a year or two ago, we also tried to do the same thing with respect to hydrology, because I think in hydrology also you have these different time scales wherein these events can play out. The extreme DT looks at much more shorter time scales, and we look at the longer time scales. But this can also be then used to really look in vulnerable regions as to what kind of risks are there in the short term as well as in the long term. And I think this would be also for me, the connection between the two.
Thank you. Anyone else? Or yes?
Just a remark. I think that in each country there is a whole ecosystem that is concerned with the alerts. I know how it works in Italy, in France. For example, in France there is Meteo France, that is the national weather forecast system, and then there are some alerts, and then it's at the level of prefecture. This level of departments that the measures are decided. So, for example, they can decide to close schools or public activities. I think that for each country, we should identify what are the stakeholders that are concerned with this kind of alerts and get in touch with them to contribute. And I can say that sometimes, at least in France, in my region, there are alerts, but not always they are precise, in the sense that sometimes we have extreme events that are not exactly in the place where they are. Or sometimes we are lucky and there's no event, or sometimes they didn't alert the good in time. It happens. So there is sometimes some things that we can improve.
Thanks for that comment, and I think Irina made the point very clearly earlier today that, of course, especially on the cases of where it's about warnings and alerts, we are working very closely with the mandated institutions on that. On the climate time scales, it often is, we're not talking about warning cases, but it's more preparation, mitigation of future events, and there the picture is a bit fuzzier. Of course, this is a good place to start, and the Met services are very tightly engaged already. Also, some civil protections in some countries, but yeah, that's part of the community. There is another question on Slido: how critical the presence of locally collected data is for the portability of the solutions. I think that may be particularly interesting in the case of you, Dirk, where you're trying to build a scalable services that might need that.
Yeah, that's a very good question, indeed. I think I made a point there of having this co-creation process and having the local people on board and having their local input. I think it's doable to create a service and translate it, but if you really want to have it picked up, then I think the local collected data, especially if you want to have real impact, you want to look at hospitalizations, mortality, these type of things, then you really need the local data involved in the project. Otherwise, yeah, you cannot go this next step. Yeah.
Joshua, do you also want to comment on that? Maybe in the case of your wind farm provider?
Yeah, for wind farm, we are much more interested on to having real-time data sets. So that like one of our key users is providing us their observation data set, but getting that high resolution in terms of temporal scale data set is very, very difficult because again, we only have confidence on one particular locations. So next time when we give this information to another, we also need this locally data set to have more trust on our applications. So that information is very, very critical.
Thank you. Are there other questions in the room? Okay. Then maybe Sebastian, you have another one?
No, it's actually something that got a bit lost in one of Sushavan's slides. So there was a sneak peek on what's to come. So you talked about historical and scenario ensembles. Like if you spotted it, there was something about 3 ensemble members. So that's actually another thing that we are working on. These are 10-kilometer resolution simulations with IFS NEMO, which are currently being produced as part of phase 2, and which boosts the sample size for better sampling of events. So that's something that we're producing at the moment, which will also become available quite soon with the other phase 2 simulations. So stay tuned for more updates on that. Just wanted to highlight that so it doesn't get lost.
Okay, so then I would suggest we thank our speakers and panelists again and close this session. You're now invited to the reception of the user exchange. I don't know, Franca, do you want to say something about that? Okay, so yeah, it is here. Please linger around. You're invited to use this opportunity. I think we've heard a lot about the importance of the events like this. So make the best of it. Make sure to find the colleagues that you need to and want to talk to, and yeah, hopefully you'll benefit from this for the next months to come. Thank you.